This program is brought to you by Stanford on iTunes U at Stanford University. Please visit us at itunes.stanford.edu.
All right, let's review a little bit. Now, I am not going to be consistent about my choice of the speed of light. Sometimes I will put it in and call it c. Other times I will just call it 1. I will try to tell you when I do and I don't. It's just formulas get too complicated when you put the c's in, and you all should be able to figure out, if I give you a formula in which the speed of light is equal to 1, you should be able to figure out by dimensional analysis where the speeds of light, where the little c's go. But here and there, I'll sprinkle in the c's, and I'll sprinkle them in when it's important, when I think that it's relevant and interesting to do so. Otherwise, I will choose the speed of light to be 1, which means we work in units like light years per year, or light seconds per second, or such units. All right, so let me review quickly. Let me just start with Galilean relativity. The Galilean pre-Einstein, Newton, Galileo relationship between reference frames, moving and stationary reference frames, is given by the simple equations which are called Galilean relativity, or Galilean transformations. For example, for motion along a one-dimensional line, the relationship between the coordinates in a moving railroad train and the stationary station are x prime is equal to x minus the velocity of the train times t, and t prime is equal to t. Time is the same for everybody, and the difference between x coordinates is just there because the origin of the moving frame is moving with velocity v relative to the stationary frame. To draw a picture, let me just draw a picture of what these transformations look like. If this is, I'll think of myself as the moving train, and I'll think of you as the stationary observers at rest. So when I speak of me, that's moving. When I speak of you, that's at rest. Of course, I think I'm at rest, and I think you're moving, and that's, of course, what relativity is all about. But let's look at Galilean relativity first. Galilean relativity, if I were to plot the time axis and the x-axis, and then on the same graph draw the t-prime axis, the t-prime axis, which stands for the location, the locus of points of the origin of coordinates for the prime moving observer, it would look at an angle, like so. And the slope of that angle, or that angle, would be controlled by the velocity of the moving reference frame. It would be, that line would be given by x, well, it's just given by x equals vt, which is the same as x prime equals 0. So that's so much for how the moving frame moves. But then if I were to plot the lines of constant time as seen in the prime reference frame, they're exactly the same as the lines of constant time in the unprimed reference frame, and so they look like that. You don't have to draw two axes for space, but you do have to draw the t-axis, and this would become the t-prime axis for the moving reference frame, for the moving coordinates. So if we made a grid, this would be the grid for the moving observer, and the grid for the stationary observer would be similar, except the lines would be vertical. These are the basic equations that govern the relationship between observers in Galilean relativity. Notice that if you invert the equations, they simply look like this. They look like x equals x prime plus vt, but I can also write that as vt prime, since t and t prime are the same thing, and t is equal to t prime. the relationship between the primed and unprimed coordinates is exactly the same as the relationship, the inverted relation, between the unprimed and the primed coordinates, with one exception. You change the sign of the velocity. That just represents the fact that if you see me moving down the track with velocity plus v, I see you moving backward in the opposite direction with velocity minus v. So that's how Galileo, if he would have written the equations, would have thought about relativity. It is the way Newton thought about it, and it's the way everybody else did until the advent of the discovery that the speed of light is the same in every reference frame. Those equations are not consistent with the speed of light being the same in every reference frame. They have to be corrected, and the last time we worked out what the rules about light imply about the corrections to those equations up there. So let me write them down for you to remind you. They are, of course, the Lorentz transformations, and they look like x prime is equal to x minus vt, exactly as Newton and Galileo might have written it, but then there's a square root of 1 minus v squared downstairs. Now, that's, if you want to put back the speed of light, let's put c equals 1 sometimes. If you want to put back the speed of light, this equation doesn't make good dimensional sense. A velocity has units of length per unit time. And a 1 has no units at all, so what you really want to do is divide this by the speed of light squared, v squared over c squared. And of course, if the velocity of the moving reference frame, the train in this case, is ordinary velocities, 50 miles an hour, 100 miles an hour, 1,000 miles an hour, even 1,000,000 miles an hour, that's quite small by comparison with the speed of light, and v squared over c squared is very negligible, even for 1,000,000 miles an hour. V squared over c squared is a very small number, and so for most practical purposes, terrestrial physics, physics not involving things moving with anywhere near the speed of light, this just becomes the same as Galilean. Square root of 1 is 1. It's exactly the same as Galilean. What about t prime? Now that was the new thing, this was the really new thing, that t prime isn't just equal to t. In other words, that time is not as universal as Newton had thought. Newton had believed in a universal time, God's time. I don't think he called it that, but we could call it that everybody has exactly the same timekeeping, and therefore t prime is equal to t. Well, that was exactly what was wrong with Galilean relativity, that made it inconsistent with the rules that the speed of light is the same in every reference frame. To correct it, Einstein wrote it that way, t, then minus Vx divided by that same square root of 1 minus v squared over c squared, but this is also not dimensionally correct. To get it to be dimensionally correct, you'll have to write velocity divided by c squared times x. Again, if the velocity is small by comparison with the speed of light, so that v over c is a very small number, then you can ignore this term, and you can ignore the v squared over c squared in the denominator, and it just reproduces t equals t prime. All right, but this is the correct formula, and it differs significantly from the Galilean formula when the velocities get up near the speed of light. In fact, when the velocity gets to the speed of light, something crazy happens here, because v equals c, v over c is equal to 1, 1 minus 1 is 0, and you're asked to divide by 0. That's not a good thing, mathematically inconsistent. And so what it tells you is that a frame of reference can never quite be moving with the speed of light relative to another one. But when it starts to get close to the speed of light, we start to see significant deviations from Newton and Galileo. Now you might ask, what about x and y? There are two other coordinates of space besides x. What about y and z? I didn't mean x and y. What about y and z? the two other components. If we're moving down the train track, then there's the coordinate of space along the track, but there's also the coordinates of space perpendicular to the track. Those are y and z. And the Lorentz transformations for them are very, very simple. They are simply that y prime is the same as y, and z prime is the same as z. In other words, coordinates along the direction of motion get mixed up with the time in this complicated way, but the coordinates perpendicular to the motion, they are the same for both frames of reference. Now, if you want to know why, just imagine having a meter stick moving on the train and a meter stick standing still, and the meter sticks pass each other, like so. Now, does an observer, and they pass each other, and they just touch at an instant of time, and the question is whether the ends of the meter sticks are at the same place. If they're at exactly the same place, then the two meter sticks will look the same to every observer. All right? The question is, will they actually pass each other? Now, the argument that says that they will stay exactly the same size goes like this. Imagine yourself in a reference frame halfway between the moving train and the stationary train. The stationary station. Right? When halfway means an observer moving along who sees me moving with a velocity and sees you moving with exactly the same velocity backwards. There's some frame of reference not moving as fast as a train, not standing as still as close to you, somebody riding a bicycle, who is sort of midway between the two reference frames, in that they see me going with velocity something and you going backward with the same velocity. That person sees an entirely symmetric situation. Entirely symmetric situation. And what he will see the two meter sticks approaching each other with exactly the same velocity. Two meter sticks in the perpendicular direction approaching each other with exactly the same velocity. And since the situation is entirely symmetric between the left and the right, there's no expectation that one of the meter sticks will pass the other one looking shorter than it. They'll pass each other looking exactly the same length. And so for that reason, there's no funny business about x and y and z, but x and t get mixed up with each other. Okay, let me show you another way to write the Lorentz transformation, which might be illuminating. It gives you a little bit of a geometric picture about how these equations work. Let's come over to this blackboard over here. First of all, let's get rid of the speeds of light in them because they're a nuisance. Let's just set it equal to 1. Just for simplicity. And now let's add these two equations on both sides. What we'll get on the left-hand side is x prime plus t prime. That's the left-hand side. What will we get on the right-hand side? We're going to get, first of all, something with the same denominator. So what we get is going to have a denominator square root of 1 minus v squared. And then in the numerator, it looks like we'll get x plus t but then we're going to get another term, which is going to be minus v times x plus t. So that will be x plus t times 1 minus v. X plus t, and then minus v times x plus t. All right. 1 over 1 minus v, 1 minus v divided by square root of 1 minus v squared. What's that? Let's work it out over here. 1 minus v upstairs, and then square root of 1 minus v squared downstairs. That's the same as the square root of 1 minus v times 1 minus v. That's just 1 minus v. I just rewrote 1 minus v, divided by the square root of 1 minus v times 1 plus v. 1 minus v squared is 1 minus v times 1 plus v. The 1 minus v's cancel, and all of this is just equal to the square root of 1 minus v over 1 plus v. Okay, so first of all, let me rewrite this equation. It says that x prime plus t prime is equal to x plus t times something which depends on the velocity, and it depends on the velocity as 1 minus v over 1 plus v. Now let's look at x prime minus t prime. All right? Now let's look at x prime minus t prime instead of x prime plus t prime, and let's see what we get. X prime minus t prime. All right, when we subtract them, we're going to get an x minus t from here, and we're going to get a plus v because we're subtracting x. You know what I want to do? I want to make a small change in this. I want to write this as t prime plus x prime. Same thing. I haven't changed anything. T plus x. It's just because it agrees with my notes. And now I want to write this one as t prime minus x prime. T prime minus x prime, that's to subtract this from this. What do we get then? We get t minus x times 1 plus v divided by the square root of 1 minus v squared. We'll get a 1 plus v because of the opposite sign that appears here. Let's see, we'll get t minus x, and then we'll get minus v times x minus t. That all adds up to a 1 plus v divided by square root of 1 minus v squared. But if you go through the same exercise here, 1 plus v, 1 plus v, 1 plus v, what you get is square root of 1 plus v over 1 minus v. It looks almost the same as the equation for x prime plus t prime, but with a slight difference that the square root that appears here is square root of 1 plus v over 1 minus v. Now, let's stop now and look at what we have. Instead of working with x and t, I've worked with new coordinates. New coordinates, x plus t and x minus t. You know what you can think of those as? If this is t and this is x, and 45 degrees, remember, represents the motion of light rays, then x prime plus t prime, or x plus t, is a coordinate along that axis, and x minus t is a coordinate along this axis. This is the x plus t coordinate, and this is the x, or the t minus x coordinate. Right? What this is telling us is that x plus t, when it's Lorentz transformed, just gets multiplied by something that depends on the velocity. And at the same time, t minus x also just gets multiplied by something, but that something is the inverse. The something here is 1 over the something here. So one picture of what these mathematical transformations are like is that t plus x, depending on whether v is positive or negative, t plus x gets stretched. That's what this says. It either gets stretched or squeezed, depending on, let's see, if v is positive, then 1 minus v is less than 1. This would be less than 1. That would say that this transformation squeezes t plus x. T prime plus x prime is t plus x times a number less than 1. So it squeezes one axis and stretches the other axis by the inverse amount. So for example, a Lorentz transformation with the appropriate velocity would squeeze this axis by a factor of 2 and double this axis by a factor of 2. That's the nature of Lorentz transformations. They're really quite simple. They're stretching along one axis, one 45-degree axis, and squeezing along the other 45-degree axis. But notice the important thing is they don't change the 45-degree axes. The 45-degree axes stay 45 degrees. Why is that important? Because that tells you that light rays continue to move with the speed of light in any reference frame. So you see, Lorentz transformations are really quite simple. They're a stretching along one axis, a squeezing along the other axis, but they preserve the 45-degree axes. They don't preserve other lines in here. Other lines will get stretched this way and squeezed the other direction, but the ones which are along the 45-degree axes are maintained. So that's the nature of Lorentz transformations, sort of a squashing of one light-like direction, an expansion of the other light-like direction along the direction of motion of the relative motion of the two reference frames. All right, any questions about the structure of Lorentz transformations before we go on? Yeah.
Back to the argument about the transverse meter stick.
Yeah.
You proved it to the intermediate observer, the two sticks under the same.
Okay.
Does that show that to the two observers who are moving?
One has to make some assumptions, but the assumption is that if two objects cross at an instant of space-time, if two events are at the same instant of space-time, and now that would mean, for example, when these two meter sticks cross each other, a flash of light could go off from the end of each one at the moment that they hit each other. We'd call that an event. If an event occurs at a particular space-time point, or if two events occur at the same space-time point in one reference frame, then they occur at the same space-time point at another reference frame. So that's an added ingredient that sort of, if you really trace every possible assumption, I'm sure there's an infinite number of assumptions, hidden things like that, but they're also easy to believe that if two events in space-time, if two events in space-time occur at the same space-time location according to one observer, then they occur at the same space-time according to another observer. The notion of an event, a point of space-time at which a thing could occur, that's an invariant concept. And so you could bring it back to the question of the events of the crossing of these two meter sticks. Yeah?
Doesn't the bicyclist also have to be in the middle of the meter stick?
In the middle of the meter stick.
So we can see these things.
Well, the bicyclist, of course, stands for a whole moving frame of reference.
He has to measure when he's at the middle of the meter stick.
Well, or he can see the flashes of light come out when the two meter sticks crash into each other. He can see the flashes of light come out and then deduce that the flashes of light came out from the same points. So I don't think he really has to be right there, but he has to be able to deduce what was going on right there by looking at the light rays. So what does he see? He sees two meter sticks come past each other and then sees a pair of flashes of light emanating from exactly the same points. Four flashes altogether, one from the right end of this meter stick, one from the left end of this meter stick, one from the right end of this meter stick, one from the left end, and sees that these two rays of light emanate from the same point in space-time, and the other two back on my shoulders here, which I can't squeeze together. I'm not as flexible as I used to be. Okay, so that's Lorentz transformations. What I forgot to do, which we'll do next time, was to show you how to compound velocities. We'll do that next time. But for the next thing, I want to tell you about proper time. Now, I don't think we talked about proper time last time. Many of you know what proper time is, some of you don't, but let's spell it out. As I said, Newton believed that time was the same for everybody. Moving, stationary, accelerated, whatever you do, time will agree. If you synchronize two clocks, whatever you do with them thereafter, they will stay synchronized. If you have a whole collection of synchronized clocks, they will stay synchronized. That, as we will see, is not true for moving clocks in the special theory of relativity. And there's a notion of time which is proper time. Now, here's what proper time means. You're going to take a walk. You're going to walk around with a high velocity, upward near the speed of light, but you carry your wristwatch with you. Okay? Everybody sitting still has their own timepiece, and the sitting still people all synchronize their timepieces so that they all agree. They synchronize their timepieces with light rays, and according to the way that Einstein described synchronizing light rays. So you people all have perfectly synchronized perfectly synchronized clocks. And I have my clock, and I start walking around. At first, when I start, I've synchronized my clock with yours. We all agree. And then I walk around, and I take a walk around the table a few times, at close to the speed of light. And at the end, I look at my timepiece, and I compare it with the timepiece of the person standing next to me over here. In general, there's no reason for them to agree, and they won't agree. The proper time of my moving clock is the time read by the moving clock. Okay? The coordinate time, this is definitions. The coordinate time is the time measured by your stationary clocks. So proper time is something which sort of follows the observer around and ticks off intervals of proper time as a clock following, as a wristwatch would tick off instants of time. All right, let me give you the formula for proper time, and then show you that proper time is an invariant concept. The proper time between two events, we're talking about now two events, we could think of them as two events along a trajectory if we wanted. The trajectory could be the trajectory of a moving clock, but for the moment, let's just think of them as two events, and one of them, for simplicity, let's take at the origin. So at the origin of coordinates. So this point over here is x equals 0, t equals 0, x prime equals 0, t prime equals 0. Notice, incidentally, where's our Lorentz transformation? We seem to have lost them. Let me write them back over here. X equals x minus v, x prime equals x minus vt over square root of 1 minus v squared. T prime is equal to t minus vx over root 1 minus v squared. Notice that when x and t are both equal to 0, x prime and t prime are also equal to 0. So we've set it up in such a way that the origin of space-time coordinates is the same for both observers. Okay, so here's our moving observer. Or let this not even be a moving observer. It's just a moving particle or a moving person. It doesn't have to correspond to a reference frame. It's just some object moving, and it could be moving with an accelerated velocity, but let's just take a small piece of its trajectory along which we can approximate it by a straight line. Okay, now, if we replaced space-time by ordinary space, if we replaced it by ordinary space, forget this and just think about ordinary space, not x and t, but x and y. We could also have different coordinates describing the same x prime and y prime, namely coordinates which were just rotated relative to the original coordinates. What kinds of things are the same for both? I'll call them observers, but I simply mean rotated coordinate frames. Well, one very invariant quantity is the distance from the origin. The distance from the origin of any point necessarily is the same in both coordinate frames. Right? That's clear. Your distance from me doesn't depend on which way I'm oriented. Right? I have my x and my y. Doesn't matter which way I'm oriented, you're still sitting 3 meters or 3 or 4 meters from me, no matter which way I turn. So that implies that the distance from the origin, the square, let's take the square of the distance from the origin, call it s squared, that's equal to x squared plus y squared. It must also be equal to x prime squared plus y prime squared. In other words, the quantity x squared plus y squared is the same in any coordinate system, ordinary coordinate system involving the rotation of coordinates. Something like that is true for Lorentz transformations. Something slightly different, a little slightly different mathematical expression this is x, this is t, and this is some point here with coordinates xt or x prime t prime, depending on which frame of reference I'm looking at that event. Right? The statement, which we can work out from this equation here, in fact, let's do it. Let's do it. Let's take the point xt, which could also be labeled by the prime coordinates, and work out the quantity x prime squared, not t prime squared plus x prime squared, but t prime squared minus x prime squared. A little bit of a glitch on what we would do if we were just rotating coordinates. T prime squared minus x prime squared. Let's write it on the right here. First of all, in the denominator, we'll get 1 minus v squared, because we've squared everything. All right, now let's look at x prime squared. That has x squared. It has plus v squared t squared, and then it has minus 2xvt. That's x prime squared, huh? That comes in with a minus sign here. But then let's add in t prime squared. T prime squared has t squared plus v squared x squared minus 2xvt, also divided by 1 minus v squared. All right, so this is t prime squared, this is x prime squared, and we subtract them. The first thing that we notice is that these things, these cross terms, cancel. When we subtract these two, the cross terms cancel. Now, the x squares don't cancel, because here we have v squared x squared minus x squared. All right, so that's minus 1 minus v squared x squared. And then what about the t squared term? There's t squared here minus v squared t squared. So that's t squared times 1 minus v squared, all over 1 minus v squared. To make a long story short, let's write it out. T prime squared minus x prime squared is equal to t squared minus x squared. Just work it out. If you didn't follow the little bit of algebra here, just work it out. Square this, subtract them in either way, and you'll find out that t prime squared minus x prime squared is the same as t squared x minus x squared. Very, very much like when you rotate coordinates, the square of the distance stays the same. The square of the distance from the origin stays the same. Now, a physicist would say that means that the quantity t squared minus x squared is invariant. It's the same no matter whether you look at it from the point of view of the primed frame or the unprimed frame. And it has a name. Because it's invariant, it's important. Anything which is invariant and which is the same for all observers must have a special importance. It's something which everybody will agree upon, and so we ought to give it a name. The name for it is proper time. The proper time between this point and this point. Proper time. The proper time between the origin and the point xt is, by definition, proper time is equal to the square root of t squared minus x squared. Why the square root? Well, it's very similar to this. It's a definition, of course. It's a definition. We could have worked with a definition where the proper time was just t squared minus x squared, but it's a definition to take the square root. But it's very much like looking at the distance between 2 points and using Pythagoras' theorem. The Pythagorean theorem says that the distance between the points is the square root of x squared plus y squared. All right, so in parallel with that, we call this the proper time between the origin and the point xt. And that, as I said, is definition, but it's a highly useful definition, and we'll see why it's useful as we go along. The main thing about it is that everybody agrees about it. Okay, first of all, let's look at some possible values that the proper time can have for various points xt. If t is bigger than x, what does it mean for t to be bigger than x? In magnitude, if t squared is bigger than x squared. If t squared is bigger than x squared, that means we're talking about points which are in a wedge here, where the time component is larger than the x component. T squared is larger than x squared, all in here. But let's in particular stay in the upper half space here. T squared is bigger than x squared if you're within this wedge. Okay. The wedge is the light cone. Oh, I should add in, yes, I should add something in. If we are working in three dimensions, three spatial dimensions, not one spatial dimension, then we should also add in minus y squared minus z squared here, minus y prime squared minus z prime squared. That makes sure that our definitions don't depend on direction in space. As long as we know that we're only talking about Lorentz transformations along a given axis, we don't really have to worry about y and z. But if we wanted to do Lorentz transformations along some other axis, and we wanted to add in y and z, we would note that this whole quantity, t prime squared minus x prime squared minus y prime squared minus z prime squared, is invariant. Why is that, incidentally? Well, remember that z prime and y prime don't transform when we go from one frame of reference along the x-axis to another. And so that doesn't make any difference if we put in y prime and z prime here, but it's a convenience to add it in, and then we have an expression here which doesn't depend on direction in space. But if you only want to think more simply about directions along a single axis, then you don't have to worry about y and z. Okay, so here we are. This point here, t squared is greater than x squared, and that means that t squared minus x squared is positive, and the square root of a positive number is another real number. So in this time-like region, this is called the time-like region because the coordinates are more in the direction of time than they are in space. In the time-like region, the proper time is just a positive number, square root of a positive number, and we take the positive square root. So t squared, so that's perfectly normal. Positive proper time up in here. What about along the light cone? Along the light cone, that's exactly where x is either equal to t or x is equal to minus t. Along here, x is equal to t. Along here, x is equal to minus t. Whoops. X is equal to minus t. So in either case, t squared is equal to x squared. So along the light cone, along the place where light rays can travel, the proper distance between, or the proper time between the origin and that point is 0. Now, this is a big difference between ordinary distance and proper time. Ordinary distance, if the distance between 2 points is 0, those points are the same point. There's no way that the distance between 2 points can be 0 and them not be sitting on top of each other. In Minkowski space, in the space describing the special theory of relativity, the space-time, 2 points can have 0 proper distance between them or 0 proper time between them and still not be the same point, here and here. Right? What is true is that if 2 points are separated by 0 proper time, then a light ray can go from one to the other. So the trajectories of light rays correspond to paths which have essentially 0 proper time along them. Okay? Real particles, sorry, not real particles, but particles moving with less than the speed of light have trajectories which are in the time-like direction like that. They're moving slower than the speed of light, and the proper time along those is positive. Now, let me prove a simple thing. Proper time measures ordinary time as seen by a clock moving with the object. For example, supposing we have a clock which is at rest. A clock which is at rest in our frame just has a vertical world line. It's perfectly at rest. Right? And for such a point, let's take a point along here, what's the proper time from the origin? It's the square root of t squared minus x squared, but x is 0 for this point. So it's just the square root of t squared, which is just t. So the proper time along a trajectory which is standing still is just the ordinary time. What does that tell you? That tells you that the proper time is nothing but the time read by a wristwatch standing still. What about the proper time along a trajectory which has a finite velocity? For example, supposing it has a finite velocity like that, and we look at the proper time for a particular point over here. Well, the principle of relativity, the equivalence between different reference frames, tells us the following thing. We could always think of this particle, object, observer, as being at rest. We could always do a Lorentz transformation. So this guy is the guy at rest. And then use the same logic that we used a second ago. In the reference frame where this is at rest, this point here would have x prime equals 0, but t prime not equal to 0. Why is it x prime equal to 0? Because in the moving reference frame, moving with this guy over here, this whole trajectory corresponds to his origin of coordinates. So x prime would be 0 for somebody moving along this trajectory here, but t prime would not be 0 over here. And we could work out exactly the same argument. The proper time to this point over here would be t prime squared minus x prime squared, but x prime squared is 0. And so the proper time along here, in the same way as along here, as along the vertical trajectory, measures the time as read by a moving watch, a moving clock. Moving clocks tick off proper time. That's the message, that the meaning of proper time is nothing but the meaning of the time as read by a watch, which is moving with the moving object. All right, so that's the notion of proper time. It's kind of funny. In these regions over here, x is bigger than t, and so t squared minus x squared is negative, and the proper time is imaginary. Points up in here are called time-like, relative to the origin. Points along the light cone here are called light-like, and points out here are called space-like. Space-like points have an imaginary proper distance, an imaginary proper time relative to the origin, but points within the light cone have a real proper time. Okay, any questions about the notion of proper time? It's very similar to distance along a trajectory, except with a funny property that there's a minus sign that you throw in here. A minus sign that you throw in instead of a plus sign. T squared minus x squared. But it has many similar properties, and in particular, it's the same in every reference frame. The proper time between two distinct points is invariant. Okay. Now, we can use that fact. We can use that fact and facts similar to it. Well, that...
Actually, the time interval between 2 points.
The time interval as read by a clock that moves between those 2 points.
Well, yeah, there's just You were using the same for both, you was using the same word for both interval and reading the clock. Never mind.
Okay. I meant time interval, but yeah. Yeah. So to put it another way, if there are 2 points in space-time and a clock, a physical real clock, can move from one to the other along a straight trajectory, that means a trajectory with constant velocity, then the difference of time readings at the 2 ends of the trajectory over here will be the proper time. In other words, the difference between the time read at this point and at that point will be the proper time along that trajectory. You can calculate then, if I give you 2 points in space-time, we can calculate very easily how long it takes to move between these 2 points as read by the moving clock, not as read by stationary clocks. That's different. As read by stationary clocks, the time difference is just whatever the time was at this point and whatever the time was at this point, where the times were just t. But the moving clock reads its own time. That's the message of special relativity, that the rate at which clocks move depends on how they move. Now we can work out in some detail the relationship between moving clocks and stationary clocks. Let's do that. And the tool is to use proper time. So let's take a clock which starts at the origin and moves along a trajectory which takes it to a point, which takes it to a point on the origin of the moving coordinates. I'm sorry, that line does not look very straight, does it? I intended it to be a straight line. Here we have our moving coordinate frame, and a clock moves from the origin to a point over here. Now, what is that point over here? That point over here is x prime equals 0. It's the origin of spatial coordinates for the moving observer. And it's some point t prime. It also has coordinates x, t. In other words, in the stationary reference frame, it has coordinates x, t. In the moving frame, it has coordinates x prime equals 0 and some t prime. I would like to know, if I know x and I know t, what is t prime? Incidentally, x, of course, is equal to vt. So really all I need to know is t and the velocity of the moving observer. Here's the moving observer. His trajectory is x equals vt. Here's t, and here's x equals vt. Okay? What is the time read by the clock moving from here to here? What is t prime? Well, now that's easy to find out. T prime squared minus x prime squared must equal t squared minus x squared. What are t, sorry, this should be prime. T prime squared minus x prime squared should equal t squared minus x squared for this point. Why? Because the expression for proper time is invariant. Okay? Same expression in either reference frame for the proper time between this point and the origin. What do I know about this point? I know that its x prime is equal to 0, so let's cancel that out. No, let's not cancel that out, let's just rewrite it. T prime squared equals t squared, but now at this point, x is equal to vt. So that's minus v squared t squared. Well, that's interesting. We now have a simple formula for t prime. First of all, let's write that as 1 minus v times t squared. 1 minus v squared times t squared. Well, we just take the square root. T prime, the time read by the moving clock, is equal to the time read by the stationary clock. The time read by the stationary clock is just this time here, times 1 minus square root of 1 minus v squared. That's the famous formula of time dilation, that when you see a moving clock, that moving clock will appear to move a little bit slow. Why slow? Because 1 minus v squared is less than 1. But everybody will agree about the value of the proper time between these 2 points, although they will disagree about the actual coordinate times. In particular, the coordinate time t prime seen in the moving reference frame will be the coordinate time in the stationary reference frame times square root of 1 minus v squared. So what that says is that the moving observer, well, the stationary observers will see the moving clock run a little bit slow. We really should at this point put in the speeds of light, c squared. V squared over c squared is typically a very, very small number. So this is almost t prime equals t, but with a slight discrepancy. This is the time dilation of a moving clock. Now, how can it possibly be that we have relativity, which says there's a complete parallel between, or a complete symmetry between the moving observer and the stationary observer? How do we then account for the fact that the stationary observer sees the moving observer having his time slowed down? What does that mean if we look at it the other way? What does the moving observer see about the stationary observer? Does he see the stationary observer's time sped up? No, also sees the time slowed down. So if I move past you with my clock seems to slow down as far as you're concerned. On the other hand, if I watch one of you, and I have all of my fellows lined up with me forming a reference frame, they will also see your clock go slow. How can that possibly be? That sounds contradictory. Well, they're talking about 2 different things. The moving observer, remember that the moving observer, his time, or his lines along which time are constant, are not these horizontal lines here. They're lines which look like this. This is t prime equals a constant. This is t prime equals a constant, and so forth. So the lines on which t prime are constant are different than the lines on which t are constant. This is this relativity of synchronicity, the relativity of being synchronous. Different observers call different things synchronous. Now, let's take the moving observer here, and the moving observer looks at the stationary clocks at an instant of his time and asks, what does the stationary clock read? Well, an instant of his time looks like this. So he's really asking not what the stationary clock reads at this point, but what the stationary clock reads at that point. So there are 2 different questions. When you ask what one observer sees of the other one's clock, there is a complete symmetry. Let's see how to say this. I think I've already said it, but let's try to say it more clearly. We're comparing different things. The surfaces along which t is constant and along which t prime is constant are different surfaces. And so when you ask whether clocks are synchronous or not synchronous and so forth, you have to account for this difference in what you mean by synchronous. That's all. So that's the time dilation, the fact that moving clocks appear to stationary observers to go slow, and stationary clocks appear to moving observers also to go slow. We could have been certain from the beginning that whatever one observer sees of the other's clock, that they will be reciprocal because of the reciprocal nature of Lorentz transformations. Okay, that's the slowing down of clocks. let's talk about the twin paradox. Somebody asked me about the twin paradox. We're now in a good position to do the twin paradox and see what it says. Let's work it out. The twin paradox, two twins are born at the origin of coordinates. One stays home, that means stays at rest, doesn't move, doesn't accelerate, doesn't move at all, and just moves along a trajectory like that, a world line like that. The other one is shot out at a high velocity, not quite the velocity of light, at a high velocity for a certain period, and then at the end of that period turns around and comes back and meets the twin at that point there. They compare their clocks. Well, all kinds of clocks they could compare. Their clocks, their watches, their heartbeats, their aging rate, their metabolic time differences between here and here, how long their beards are, or whatever corresponds to a good clock. They compare their clocks at this point and ask what the relationship between the time read by a clock moving here and a time read by a clock moving here. Well, we're all set up to calculate it now, because all we have to do is to calculate the proper time between this point and this point along the vertical trajectory and the proper time along this trajectory, which consists of two different pieces. We just add up the proper time from here to here and the proper time from here to here, and that will tell us what the clocks measure. Clocks measure proper time. All right, first of all, this triangle, assuming that the second twin comes back with the same velocity that he was shot out with some velocity v, then this triangle is a nice isosceles triangle, and we can divide this vertical line in half, call this side t, this half side t. It takes, therefore, time 2t from the stationary person here. It takes time 2t to go from this world point to this world point, and therefore the person who stays home says it took amount of time twice capital T for my twin to return. All right, so that's twice capital T. That's what the observer who stays home says the time interval between birth and meeting the twin is. Now, what about the twin who goes out and comes back? Let's calculate what the total proper time is along this trajectory here. He goes out with velocity v. How far out does he get? He gets out a distance v times t. V times t is the distance along the x-axis that the moving twin gets out. So this point then has coordinates x equals vt and time t. Let's calculate the proper time from here to here. The proper time, the square of the proper time, is t squared minus x squared. So the proper time along the first leg of the journey here is t squared minus v squared t squared, which is equal to 1 minus v squared times t squared. That's the square of the proper time. We have to take the square root of it to find out how much the clock changed from here to here. And so the time change, the proper time along this trajectory here, is square root of 1 minus v squared times t. What about on the second leg of the journey? The second leg of the journey is exactly parallel to the first leg of the journey, except going backward. The proper time between here and here is exactly the same as the proper time between here and here. There's the same x coordinate and the same t. So the answer for the observer going along this bent trajectory here is twice this. Twice t times square root of 1 minus v squared, as opposed to just twice t. Right? Which one is smaller? The smaller one, the smaller proper time, is associated with the twin who got shot out and came back. Why? Because 1 minus v squared is smaller than 1. So the amount of time read off by the moving clocks here is smaller by factor square root of 1 minus v squared than the time measured along the trajectory of the twin who stayed home. All kinds of times, as I said, the length of a beard, the number of heartbeats, all sorts of things, the time read along this moving trajectory will be less, and the consequence is that the moving twin comes back looking younger, feeling younger, looking younger, being younger than the twin who stayed home. Now, is this a paradox? It's not a paradox because there's nothing inconsistent about it. It doesn't look inconsistent. There's nothing particularly inconsistent. Sometimes people ask, how do you tell which twin moved and which twin didn't move? Well, that's not hard. This twin reversed its trajectory and accelerated at this point over here. And so if they were in a rocket ship, they would feel the rocket ship accelerate, and there is no symmetry between the two twins. One twin just stays at home, experiences no acceleration, experiences no tendency to be thrust back and forth by the acceleration of whatever he's sitting in. The other twin suddenly experiences a sharp acceleration at this point, and so there's no symmetry between them. There's no more of a contradiction than asking about the sides of a triangle. The distance along the side of a triangle is not the same as the distance along the broken path composed of the other two sides. There's nothing more paradoxical than that. The proper distance along the sides of these two triangles, broken trajectory here, is just different than the proper distance along here. Now, Newton would not have understood that, or at least probably Newton would have understood it if it was explained to him. He was certainly smart enough. But with his own view of time and his own view of space, this would have been a shock to discover that a twin that goes out and comes back younger than the twin who stayed home. Yeah, question?
Typical question. So at that point there, the physics is now different.
Well, the twin feels something quite different.
How does one argue around the fact that there are accelerations there?
No, you don't argue around it. There's acceleration there.
But well, then you don't know any longer if this analysis about clocks is correct.
Okay. The assumption, first of all, you can smooth this out. There was nothing very special about making this a sharp turn. All right? All right. To say that it's smoothed out just says that there's a finite acceleration rather than an instantaneous infinite acceleration. All right, that's good. As I said, the assumption is that the clocks that we have, the way that they tick is insensitive to acceleration. All right, now this isn't true of real clocks. Real clocks, if you accelerate them too hard, they'll break. All right? If you accelerate your clock real hard, you'll break it. Now, it also depends on the size of a clock. The bigger the clock is, if you give it a hard acceleration, the easier it is to break it. If you take a tiny, tiny, tiny little clock and you accelerate it, it's harder to break. Taking an atom and accelerating it at 10 meters per second, the atomic clock that's composed of the electron going around the nucleus is not going to be affected by that 10 meters per second. On the other hand, a great big clock, 100 miles wide and so forth, that you try to accelerate it, it's going to be very, very delicate to accelerate it without changing the way that it ticks. Okay? So the assumption is that the clocks tick off proper time. Right? That's an assumption, that good, faithful, small clocks, which are very well built and built to withstand acceleration, that they simply tick off proper time. If they tick off proper time, all we have to do is measure the proper time along there. Now, as I said, we can do this experiment in a way that minimizes the amount of acceleration here. We don't need a lot of acceleration. We can have during this period here, the acceleration be very modest. It could be a small fraction of the 10 meters per second that we feel in this room here. We don't normally think that that 10 meters per second has any very big significance and any big effect on our wristwatches. If we swing our arm around a little bit, we can swing it around at more than 10 meters per second. If the clock is built to withstand shock and so forth, then the acceleration won't have much effect on it. And so the assumption is that the acceleration doesn't have much effect on the clock, and the meaning of that is that the clock always ticks off proper time. So it ticks off the number of units of proper time along the trajectory. Now, that is an assumption. That is an assumption. It's the assumption of an ideal clock. It is what you mean by an ideal clock. Does that help?
The thing is,
No.
the thing is that my impression is
Yeah.
that all of this follows some very, very careful analysis of the kinematics or whatever you call it.
Yeah.
Without accelerations in them.
Yes.
And light signals.
Yes.
So.
Right.
It's a little tough. It seems to
Right.
me like the analysis in a way breaks down there.
The logic of the analysis has to be supplemented with some additional physical facts that I don't think you can derive just from what we said. But we derive them from the experience of knowing that if we have a small clock, well-made, built to resist shock and so forth, that as a matter of experience, we know that that clock's rate of ticking will not be sensitive to modest accelerations, will not be particularly sensitive. Yeah?
You did this in general relativity, and you only got gravitational. So if you threw a clock up and let it come back down,
Yeah.
you would get the same sort of answer, or if you slung it around the stars or like.
Yeah, but would you kid? No. You see, it's not going to help to say general relativity, because then what you're going to be asking is what is the effect of the gravitational field on the way the clock behaves, right? And I can't answer that unless I know more about the clock. I have to know the details of how the clock works and so forth. Again, if the clock is a big sloppy clock made out of very big components and components which aren't very rigid and so forth, then it's going to be very sensitive to acceleration on the one hand, but it's also going to be, if I put it on the table here, it's also going to be squashed down by the gravitational field, and so it will also fail to be a good faithful clock. If I take a small hard clock, by hard I mean hardened against acceleration, then number one, it will report faithful timekeeping if I put it on the table in the gravitational field. Number two, it will report faithful timekeeping if I swing it around my head on a rope. But I can't prove that from the things that we've done, from the mathematics we've done. I can say that's a matter of experience and a matter of physics and a matter of how clocks are made and what they're made out of and so forth.
Yeah, but what you've been talking about here is what I would call, say, the mechanics of the clock.
Yeah, you have to, right.
But there's the other thing, which is, I don't know the proper word, the fabric of space under acceleration.
Right.
Which is a different.
Okay, right. So if, to the extent that we talk about the fabric of space, what we would be talking about here would be proper time measurements along this trajectory here. The fabric of space, or whatever the right word for it is, the geometry of space-time. The geometry of space-time is a geometry of proper times and proper distances.
What you're saying then is I can reduce the thing to small intervals, so
Yeah.
within,
Yes.
within each interval.
Absolutely. That was implicit. I should have made that explicit. Yes, absolutely, indeed. Yes, yes, I should have been explicit about that. Right. We divide the trajectory into small little segments, each of which has approximately a very constant velocity along that little segment. We calculate the proper time along that segment. We add it to the proper time along the next segment. We add it to the proper time along the next segment. But it's very, very similar mathematics to the way that we would calculate the length along a curve. We calculate the length along a curve by dividing it up into a lot of little intervals, and for each interval, calculating the length by x squared plus y squared, or delta x squared plus delta y squared, square root, add them all up, and that gives us the length along the curve. In very much the same way, we take this curved trajectory and we divide it into small little intervals. Each interval can be thought of as almost a straight line, and therefore each interval can be analyzed by thinking of it as having a constant velocity, and along that trajectory we add up all the constant times. Is that what the question was? Is that why we were... No, I know exactly what you're asking. The way to analyze that is to imagine actually sending light rays back and forth. Let's tick off some time intervals here. Well, let's imagine ticking off 1 second intervals along both trajectories. 1 second intervals of proper time along both trajectories. So here 1 second intervals might look something approximately like this for the stationary person. This isn't very many seconds, so it's not going to grow a very long beard. All right. And 1 second intervals would be longer along here because the moving clocks appear to go slow to the stationary observer. They might go a little bit faster in this. All right, so it look like that. Okay, now we could start sending light signals back and forth. Every instant, the stationary observer could send a light signal to the moving observer. Now look what would happen. The first set of light signals that were sent early would come to the moving observer stretched out. This is Doppler shift. This is Doppler shift, in fact, but we don't even have to think about it as Doppler shift. If this guy is moving fast, he sees the light coming, the series of light pulses coming from the stationary observer, coming delayed, very delayed at first, and then all lumped up, not delayed, but squeezed together in the second part of the trajectory here. So he sees all the light signals, the 1, 2, 3, 4, 5, 6, or 6 or 5 light signals, but sees the first set of them come very slowly, and the last set of them come very quickly. Now, what about the stationary observer looking at the moving observer? The moving observer may also send out light signals. And also there would be kind of Doppler shifts, but the number of light signals that the stationary observer sees would equal the number of light signals that the moving observer sent out, and the number of light signals that the moving observer sees would equal the number of light signals that the stationary observer sees. So in both cases, they would see something taking place somewhat irregularly in time. At first they would see things stretched out and slowed down, okay? And then they would see things speeded up in both cases, but at slightly different rates, and rates which you can calculate. But they won't see any missing frames. By missing frames, you would mean missing light signals. They would see each one would see all the light signals that the other one sent out, but coming at rates which would depend on their relative state of motion. Does that answer your question?
It sort of answers it. When you're talking about Doppler and something else kind of bothers me. If the person, the astronaut coming back, sees the light shifted, let's say the first person, the first twin, he transmits light that's of a low frequency.
This person transmits light of low frequency, yeah.
The person coming back, when he collects the light, would he be collecting more energy than was, I mean, I'm sure the answer is no, but it sounds like he would be actually collecting more energy.
Okay, before we can answer that, we have to know more about energy. So let's wait on that kind of question until we know something about energy. At the moment, all we're talking about is X's and T's. But it's a reasonable question. How does the energetics appear to both observers? An answer is that energy really only makes sense in the usual sense to an observer who is not accelerated. To talk about the energy of the moving of the accelerated observer is very tricky, and yeah.
So, not particularly
You got to talk loud.
not particularly the relativity question is what you mentioned here, but in previous classes you talked about theories like tensor line, string theory that have a concept of spatial dimensions that are curled up. Now in that case, you could have the two twins if they were moving, if the moving twin was only moving along the dimension that was curled up, you could have them meet without any of them actually accelerating. So
Without any of them doing what?
without either of them accelerating.
Oh. Yes, but there would nevertheless be an asymmetry between the one that went around the direction and the one who stood still.
So how would they notice that?
Well, the moving observer would discover a surprise. He would discover that he kept repetitively passing through the same places. If we were moving on a circle, we would discover that repetitively we keep passing the same place. I have to think about that. That's a good question, but the answer is definitely that they're asymmetric. The person moving around the closed loop and the one standing still. Yeah.
The guy is moving around since the other guy is moving around.
No. That is not quite right. Let's come back to it. I need to think about a good answer to that. It's a nice question. Give me some time to think about it. I don't want to give you an unthought out answer, so let me come back to it. Does everybody understand what the question was? The question is an interesting one. Yeah. Supposing you lived in a world of 2 dimensions of space. 2 dimensions of space. This was only a world of 1 dimension of space. And your world was a cylinder of space. Okay? Now, this is space. This is not space-time. You can imagine such a world. Special relativity doesn't actually quite make sense for it. There's a problem with special relativity here. But let's suppose perfect special relativity made sense. Then an observer could stay home over here, and another one could move around in a trajectory that, this isn't time. Vertical isn't time. Vertical is space. One observer could just stand there, stand still, and the other could go around at a large velocity and then come back. That observer who was moving around with a large velocity, it would be unnecessary for him to experience any acceleration in going around here, just moving with the same velocity, and would leave and come back without ever having experienced any acceleration. However, it is not true that they wouldn't experience the fact that they were on the closed contour. They would, yeah.
You could experience radial acceleration, right?
Sorry?
You would experience radial acceleration.
Moving around in this closed curve here? No. This, okay, I see what you're asking. No, you're not living in a world which is a solid cylinder in which the radius means anything. You're just living in a world which is just a pure surface. A pure surface. There's no notion of distance from the center here because there's nothing in there. Let's come back to it. This is way beyond what I wanted to discuss today, Kaluza-Klein theory. This is not a somewhat more advanced question. What I did want to get to before we quit is length contraction. We did time dilation by doing proper time. We do length contraction in a very similar way. let's look, the first thing when you want to understand the special relativity problem is draw a picture. Always draw a picture and see if you can't cast your question in a diagrammatic language which you can then answer by using Lorentz transformations and that sort of thing. So let's begin. Always start that way. Always. For reference, we put in a light cone. That's the speed of light. Nothing moves faster than the speed of light. Okay. Now we have our moving observer. We have a stationary observer. We have our moving observer. Here's the trajectory of the moving observer. Here is the surface of constant time. This is t equals vx. This is x equals vt. One of these is a surface along which the moving observer's clocks are all synchronized. This motion here is just the origin of coordinates, or the origin of spatial coordinates of the moving observer. And now let's imagine a meter stick. Let's take a meter stick which is at rest in the rest frame. So I need another color. Let's see, red may do. A meter stick which is at rest has two ends. Let's take the left end of the meter stick. The left end of the meter stick might start over here, and it's at rest, so the left end of the meter stick is over here. The right end of the meter stick is at x equals 1, and it's over here. The meter stick sweeps out a space-time strip. At each instant of time, the meter stick is 1 meter long, but as time moves on, the meter stick sweeps out a kind of ribbon through space-time. All right, now we want to know how long the moving observer says that the meter stick is. How long is the meter stick according to the moving observer? Now, what does the moving observer mean? The moving observer means by the length, and this is, of course, a definition to some extent. The definition of the length of the meter stick in the moving frame of reference is the following. You take the two ends of the meter stick at the same instant of time, but whose time? The moving observer's time. The moving observer takes the two ends, or looks at the two ends of the meter stick at a synchronous time in his own reference frame, and asks in his own reference frame how far apart is the front end of the meter stick and the rear end of the meter stick at a given instant of time. Well, a given instant of time in the moving reference frame means this t equals vx trajectory over here, or this t equals vx surface over here. So here's one end of the meter stick at that instant of time. Here's the other end of the meter stick at the same instant of t prime, if you like. In the stationary reference frame, these 2 points are synchronous. In the moving reference frame, these 2 points are synchronous. So if we want to know how long the meter stick looks in the moving reference frame, what we want to know is not what the x of this point is, but we want to know what the x prime of that point is. We want to know what the x prime of that point is, which would be what the moving observer would call the length of that meter stick. Now, there's an easy way to find out. Well, one way to find out is just to compute where this point is and then do a Lorentz transformation to find out what x prime is. But there's an easier way, and it's just to use proper distance. Proper distance means t squared minus x squared, or the square of the proper distance, t squared or x squared minus t squared, it doesn't matter, one or the other, and use the fact that they're the same in the two reference frames. So let's take this point over here. What is its proper distance? I won't call it proper time because it's not time-like, but instead of looking at t squared minus x squared, we could look at x squared minus t squared, it doesn't matter. What is the invariant distance, four-dimensional or space-time invariant distance between this point and that point? Well, on the one hand, if I work it out in the primed frame of reference, it's just t prime squared minus x prime squared. That's the square of this proper interval here, where this point has coordinates t prime and x prime. But what's the t prime of this point? The t prime of this point is 0. This is the surface t prime equals 0. This whole surface corresponds to the origin of time coordinates for the moving observer. So along here, t prime is equal to 0, and the proper distance from the origin is just, or the square of the proper distance is just minus x prime squared. On the other hand, let's find the unprimed coordinates of this point. This was supposed to be a meter stick, 1 meter long, so this corresponds to x equals 1. X equals 1 in the stationary reference frame, the stationary meter stick, and the stationary reference frame is exactly 1 meter long. So this point corresponds to x equals 1, this whole trajectory here. What about the height of this point? That's t. All right, that's t equals vx all along this trajectory. So along here, t is equal to just v. T equals vx, but x equals 1. So along here, this point here is x equals 1, t equals v. All right, so on the left-hand side here, we have the proper distance expressed in terms of primed coordinates. Let's express it now in terms of the unprimed coordinates. That's going to be t squared, which is v squared, minus x squared, which is 1. So what do we find out? We discover that the primed space coordinate of this point over here is x prime is equal to the square root of 1 minus v squared. I've just changed the sign and taken the square root. Well, that says that the meter stick, which is at rest in your frame of reference, in my frame of reference appears to have length square root of 1 minus v squared. In other words, the coordinate distance between the two ends of the meter stick in the moving reference frame is square root of 1 minus v squared. X prime at this point is 0. X prime at this point is square root of 1 minus v squared. So you see what that says. That says that the stationary meter stick is seen in the moving reference frame as having a shorter length. Again, an application of the invariance of the proper distance. T prime squared minus x prime squared is equal to t squared minus x squared. That's what I've used. All right. Let's just go through it again. For this point, or first of all, for the first point on the left here, everything is equal to 0. X, t, x prime, t prime, they're all equal to 0, and that's trivial. For this point, on the one hand, t prime is equal to 0, so we cross this out. On the other hand, x is equal to 1 and t is equal to v. So that gives us the 1 minus v squared over here, and it tells us that x prime is equal to square root of 1 minus v squared. So the comparison of the length of the meter sticks in the two reference frames says that when a meter stick is at rest, a moving observer sees it as being shorter. Of course, the converse is also true and could be worked out in a similar way. The moving, what did I say? We said this, the stationary meter stick looks short to the moving observer. The moving meter stick looks short to the stationary observer. That's the reciprocal character of Lorentz transformations. Okay, any questions about length contraction, time dilation, Lorentz transformations, or any of the geometry that we've done? Yeah.
Does anything go the speed of light except light?
No? Well, yes, gravity.
Do we know that?
No. Do we know it? Well, We certainly know it within the framework of the general theory of relativity, yes. Yes, within the framework of the general theory of relativity, yes. Do we know it as an experimental fact? We really have never directly seen gravitational waves. We'd like to see gravitational waves, but what we have seen is that the effects of gravitational waves coming from binary pulsars, and what's known about that tends to suggest, not terribly strongly, that light and gravity travel with the same speed. So no, there's no direct experimental evidence that gravitational waves travel with the same speed as electromagnetic waves. On the other hand, Einstein would have had to have been very wrong for it to be untrue. Yeah.
From the perspective of, say, an astronaut, he can actually accelerate faster than light.
You don't wait. Accelerate faster than the speed of light doesn't mean anything.
I mean, travel, as in, let's say they wanted to get from here to another star that's, say, 10 light years away.
Yeah.
They could, from their own reference frame, get there.
In less than 4 years.
Yeah.
Yes, that's true.
Okay.
Yes, that's true. And the way to see that is, okay, so here's a moving observer. Here's a moving observer. Here's star number 1. Here's star number 2. And that's 4 light years away or whatever. We want to find out how long, not in our stationary reference frame it takes to get here, but how long does the moving observer say that it takes. And for that, we have to calculate the proper time between here and here. Now, the point is that the proper time of this point may be t and x. The point is the proper time, which is t squared, the square of the proper time, is t squared minus x squared. That means it's always smaller than just t squared by itself. So the proper time between here and here is less than the actual coordinate time. So for that reason, yes, you're absolutely right. This person over here would say that it takes less time than the 4 light years or whatever it would be that the stationary observer would.
So from his perspective, wouldn't it also be right to say that the star actually came to him faster than?
Well, what the moving observer would say is that he would put himself, first of all, in his own frame of reference, and then he would look at the 2 stars, and he would see that the 2 stars were a lot closer together than what the stationary observer said. So he would say it took a short amount of time to go from one to the other. In other words, the moving observer would see the Lorentz contracted distance between the stars, and so would conclude that it took a small amount of time to go from one star to the other.
But to him, that length contraction, wouldn't it look like the stars are traveling faster than the speed of light?
No, the stars would not appear to be traveling faster than the speed of light. They would appear to be traveling with exactly the opposite velocity. The stars see the astronaut traveling with a certain velocity, and the astronaut sees the stars traveling with exactly the negative velocity
But when he starts out, when he looks at this and observes the star, and measures the distance to be 5 light years, then he...
Yes, but you have to ask, when he's moving, how far apart does he see the stars? And if he's moving with close to the speed of light, then he sees the stars as being not 5 light years or 4 light years or whatever we said, but 4 light years times the square root of 1 minus v squared. And that, in his reference frame, would be the description. So...
The trip looked like it was 5 years away, and a few minutes later, it looked like it was 2 light years.
Which, sorry, why does...
When you start out, before you accelerate, the star looks like it's 5 years away. Then you accelerate, and
okay, so...
it looks like it's 2 light years.
Okay, you're correct. But then we have to analyze a more complicated problem. The complicated problem then starts with an observer which is at rest. And again, the observer starts to accelerate and has to accelerate up to this velocity, and we have to take into account this effects of acceleration. The simpler calculation to do is to imagine an astronaut that was always, forever and ever moving with uniform velocity. Remember, the special theory of relativity, just like Newton's theory, only makes sense in inertial reference frames. To find out what happens in a non-inertial reference frame, we can answer the question. We can answer the question, but the question will not be answered by application of exactly the same formulas that we would use in an inertial frame.
And you started off by saying the speed of light is always the speed of light in accelerated.
Yeah, absolutely. Yeah, everything we've been talking about is in inertial reference frames. To study non-inertial reference frames, we have to begin over again. And as you correctly point out, there's obviously going to be some effects of acceleration which we have to take into account. Okay. Yes?
So you would have, so the twin paradox, say, for example, if a rocket took off and had to accelerate, you would still get the same end product, but you have to, it'd be more complicated.
Wait, sorry, again.
I mean, the twin paradox.
Yes.
If the person, if the twin that took off in the rocket had to accelerate to.
Oh, yeah. I mean, if he wasn't born moving with a large velocity. Yeah. Right. But you would still do the same thing. You would still calculate the total proper time along his trajectory. Yeah. So the total proper time would have contributions from different velocities, and we can work those out. They're simple to work out. But yes, right. Now we assume one twin is born with a huge velocity and the other one is at rest. Oh, the poor woman. I mean. Very male audience today.
Not to dwell on this issue of time, but it seems that all these problems that we have are generated by the fact that we put time in such a special place, when in fact...
Well, we're going to see that time is not in a special place. Yeah, you're right. In the back of our minds, we tend to isolate time as special, but the lesson of special relativity is that time is not that special. But the real question is, can we recover all of the physics of slow velocities that we normally know and learn and love from our Darwinian circuits that we inherited from all the years that nothing ever moved faster than 50 miles an hour? Can we recover it by taking the formulas from special relativity and specializing them to the case of very slow velocities? And yes, of course we can.
But I've also come to think about it in a little bit different way, which is not only that it's special, but it's sort of elevated to the level of a special dimension, if you will, a fourth dimension.
Well,
Is this
yes.
necessary? I mean,
Is it necessary? It's not only not necessary, Einstein never thought about that. He never said the time was the fourth dimension. It's not necessary to think of time as the fourth dimension, but once you start mixing it up with space, where are our Lorentz transformations here, there's an awful lot of the physics which looks very symmetric between space and time, sort of pseudo-symmetric, t squared minus x squared minus y squared minus z squared. They do get mixed up with each other under Lorentz transformations in a way that they wouldn't under these Galilean transformations. So here you see, in Galileo, time really just is time, whereas in Einstein or Lorentz, time really does, oh here it is, time really does get mixed up with space in a way that makes you not want to think of it as fundamentally separate. Decoupled, yeah. Yeah, they're geometrically part of a whole which is bigger than either of them, yeah.
If I have a hydrogen atom in front of me, I see a particular value.
Yeah, you know, I think if we want to get in there, we better get in.
I'm sorry. I have to
The preceding program was brought to you by Stanford on iTunes U and is copyrighted by the Board of Trustees of the Leland Stanford Junior University. Please visit us at itunes.stanford.edu.